Have you ever wondered, when you open a browser, listen to music or play games, how your computer manages to run all these programs in a tiny piece of memory in an orderly manner? Why can your computer run dozens of applications even though it only has 8 gigabytes of memory? Today, we're going to thoroughly explain how does the operating system manage memory. We'll start from the history and gradually dive into key mechanisms like paging, page tables, and virtual memory. In early computers, such as those in the 1950s and 60s, computers had just been invented and there was no concept of operating systems. At that time, memory was like a blackboard, programs were written into it and erased after execution. There was no isolation or protection. A single bug could crash the whole system. In the 1960s, commercial computer manufacturers developed batch processing systems, creating different operating systems for different models. In batch processing systems, memory management adopted a contiguous memory allocation method, assigning each program a block of contiguous physical memory. But this led to serious external fragmentation problems, where memory was split into non-contiguous free blocks. Even if the total space was sufficient, large programs couldn't get the contiguous memory they needed. For example, in 1 megabyte of total memory, even if there are multiple 100 kilobytes free blocks, a program requiring 500 kilobytes of contiguous space would still fail to load. Also, programs needed to be fully loaded into memory, leading to low memory utilization. In the 1970s, the paging mechanism came onto the historical stage, breaking the limitations of contiguous memory allocation and enabling flexible memory allocation and efficient utilization. Paging divides both memory and programs into fixed-sized blocks called pages and page frames, and uses an address translation mechanism to achieve non-contiguous storage. Programs no longer need contiguous space. Pages can be scattered across memory like puzzle pieces. The birth of paging marked the liberation of computer systems from the limitations of physical memory and ushered in a new era of software-defined memory. In the 1980s, as programs grew more complex, paging solved external fragmentation but introduced a disconnect between logical structure and physical storage. Paging treats a program as an unstructured byte stream, ignoring its logical modules. Moreover, paging uses fixed-size pages, whereas program modules vary in size. For example, code segment 100 kilobytes, stack segment 50 kilobytes, causing mismatches between allocation granularity and logical modules. Thus, segmentation was introduced, dividing programs by their logical functions into different segments such as code, data, stack, and heap. Each segment has an independent name and length, and the segment table maps logical addresses to physical addresses. Segmentation marked a key transition from hardware-oriented to software-oriented memory management. Its combination with paging formed the foundation of modern OS memory management. In the 1990s, more issues began to surface. First, hardware limitations. DRAM was expensive. For example, in 1990, 16 megabytes cost $200, while program sizes were growing exponentially. For example, Windows 95 required 8 megabytes plus, and large games began to consume tens of MBs. Second, the demand for multitasking surged. GUI operating systems like Windows 95 and Mac OS 8 needed to run multiple applications simultaneously. Physical memory allocation could no longer keep up. The core problem was, how can small memory run large programs? Thus, virtual memory was born. By dynamically swapping between memory and external storage, physical memory was extended into a logically infinite space. Virtual memory is essentially a memory abstraction technology. Through collaboration between hardware and software, the virtual addresses seen by programs are mapped to physical memory or external storage, like hard disks. With this, the combination of paging and segmentation, along with the widespread adoption of virtual memory, brought computers into an era where programs believe they have infinite memory. In modern OS, virtual memory abstracts physical memory. Every program sees fake memory addresses, enabling processes to use more address space than physical memory. The core mechanism is still based on paging. By dynamically swapping between memory and external storage, this abstraction is achieved. The OS divides a process's address space into fixed-size pages, commonly 4 kilobytes. Physical memory is also divided into equal-sized page frames. Pages are logical units. Page frames are physical units. They are the same size to facilitate mapping. Each process maintains a page table, recording the mapping between logical pages and physical page frames. When a program accesses page N, it first looks up the page table to find the frame, then converts to the physical address. For example, for a virtual address 0x2f3a, it belongs to page 2. The page table tells us it's in physical frame 6, and the final address is obtained by adding the offset 0x3a. Although programs access virtual addresses, they ultimately access the physical RAM addresses. The conversion is done by the page table. The page table is a core data structure in OS memory management. Each entry corresponds to a logical page and records its mapped physical frame and status. The simplest page table is a single-level page table. Each process has a linear page table, and the page number directly indexes into it. But large address spaces make this memory heavy. For example, on a 32-bit system with 4 kilobytes pages and 4B entries, the page table needs 4 megabytes of memory. To reduce memory usage, multi-level page tables were introduced. Logical page numbers are split into hierarchical indices: top-level directory, secondary directory, page number, and offset. Multi-level page tables are like dictionary directories. creating layers only as needed, minimizing memory overhead. For example, the x86 to 64 4-level page table divides virtual addresses into 4 indices and loads only the active page tables. As mentioned earlier, virtual memory works by dynamically swapping between memory and storage, using the disk to impersonate RAM. This is what the OS constantly does in the background. First, demand paging. When a process starts, only necessary pages are loaded, others stay in storage. Accessing an unloaded page triggers a page fault, and the system loads the page from storage into memory. Second, page replacement. When memory is full, the OS selects pages to evict and bring in new ones, keeping frequently used pages in memory. Common replacement algorithms include: first in, first out. It evicts the oldest page. Uses a queue of page load order. Second, least recently used. It evicts the least recently accessed page. Assumes what's been unused will likely stay unused. Can use timestamps or doubly linked lists to track usage. Third, clock. A simplified LRU using access bits to simulate recent use, avoiding complex data structures. Others include LFU, MRU, LRUK, 2Q, etc. Modern OS divide memory into kernel space and user space. Kernel space has the highest privilege, can execute all CPU instructions, access all physical memory, including other processes, run kernel code, device drivers, interrupt handlers, and control all hardware resources. All processes share the same kernel space. User space has lower privilege, is prohibited from directly accessing hardware or sensitive resources, and can only access its assigned virtual memory. Access is restricted by page table permissions. User space runs application code, browser, game, office software, and must request resources via system calls. Each process has isolated user space. Memory is sandboxed. User space can't directly access kernel resources. It must go through system calls. Firstly, user program makes a request, for example, read a file via read function. Then, trapped to kernel mode, CPU switches to high privilege mode via interrupt, saving user context. Next, kernel handles the request. OS executes the service routine based on system call number. For example, read is syscall 0. Finally, return to user space. Result is returned. CPU switches back to user mode. During this process, the OS uses the interrupt vector table to map syscall numbers to kernel functions, page table permission bits to block user access to kernel space, and registers or stack to pass parameters between spaces. The separation between kernel and user space is fundamentally a security mechanism implemented by virtual memory page tables and CPU privilege levels. This design ensures both system stability and developer convenience. Applications don't need to worry about hardware details, just make system calls. From single tasking to multi-threading, from single machines to distributed systems, this architecture remains the core pillar of modern OS. In conclusion, the OS's memory management system is like a smart dispatcher or hotel front desk. Each program is a guest. The virtual address is the room number they receive. The physical address is the actual room. The page table is the front desk ledger, responsible for mapping and scheduling. Not enough rooms? Move someone out. Need to return? Move them back in. It's thanks to these mechanisms that modern OS can switch freely between dozens of applications, dynamically expand, schedule automatically, and still ensure both security and efficiency. That's all for today's video. If you found this content packed with value, don't forget to like and subscribe. If you want to dive deeper into page table details, Linux memory allocation, or cache coherence, let me know in the comments. See you in the next one.